Welcome back to my YouTube channel. In this class, I am going to discuss about throttling devices, which are another kind of steady flow devices that I am going to discuss. And I will also derive the steady flow energy equation for throttling devices. Before starting, I must say one thing to all of you. Please do subscribe to this channel and of course like it and share it to your friends. Let's get started. So what is throttling valve? First of all, we must know what is throttling devices or throttling valves. They are nothing but they are flow restricting devices. They are flow restricting devices. Flow restricting devices that cause significant pressure drop in a fluid. So then question must be coming into your mind, अगर ये प्रेशर ड्रॉप हो रहा है इस डिवाइस में तो टरबाइन में भी ड्रॉप होता है और नोजल में भी ड्रॉप होता है एंड वन मोस्ट इंपॉर्टेंट थिंग इज दैट थ्रॉटलिंग वाल्व इज ए स्टेडी फ्लो डिवाइस एंड नोजल एंड टरबाइन आर ऑल्सो स्टेडी फ्लो डिवाइसेस. सो यहाँ भी देर इज सम प्रेशर ड्रॉप एंड नोजल में भी प्रेशर ड्रॉप हो रहा है, टरबाइन में भी होता है. तो व्हाट इज द बेसिक डिफरेंस बिटवीन थ्रॉटलिंग वाल्व एंड द नोजल एंड द टरबाइन, दैट वी विल discuss. So first difference is, you see, in nozzle what happens, the pressure drop in nozzle, the pressure drop results in increase in kinetic energy or velocity of fluid. Velocity of fluid. We know that nozzle is a device which increases the velocity of a fluid at the expense of the enthalpy of fluid, and in this process also there is a decrease in the pressure of the fluid. So velocity बढ़ जाता है और प्रेशर घट जाता है in nozzle. So one form of energy is converted into another form. And what happens in turbine? In turbine, pressure drop. Here pressure drop means pressure drop in the fluid that passes through devices. The pressure drop of gas that passes through nozzle is converted into increase in kinetic energy or velocity. We know that kinetic energy is half mv square. In case of turbine, what happens? Pressure drop results in control volume workout, control volume work, or you can say shaft work, or you can say shaft work. That's the key point. You see here, in case of nozzle, pressure drop results in increase in velocity or kinetic energy. But in case of turbine, you know, turbine is a power producing device. So pressure drop जो फ्लूइड टर्बाइन में पास करता है उसका pressure drop takes place, but that results in some control volume work. You know, turbine is a power producing machine in contrast to compressor which is a power consuming machine. So control volume work मतलब shaft work, क्योंकि shaft लगा होता है. So control volume work is same as shaft work. So this is the basic difference. But ये दोनों डिवाइस में, नोजल और टर्बाइन में, प्रेशर ड्रॉप results in some increase in the nozzle, it results in increase in kinetic energy, and in case of turbine it produces some shaft work or control volume work. प्रेशर तो ड्रॉप होता है लेकिन ये सम कंट्रोल वॉल्यूम या शाफ्ट वर्क प्रोड्यूस करता है. बट इन केस ऑफ थ्रोटलिंग valves, no useful work or neither any useful work nor any increase in kinetic energy is produced. That is the basic difference. In nozzle, some kinetic energy, increase in kinetic energy takes place, and in turbine, some control volume work is produced. But in case of throttling valve, pressure drop takes place. Pressure drop in the fluid that passes through these flow restricting devices take place, but without any increase, without neither increase in kinetic energy nor any control volume or shaft work. सो ये जो तो तुम पूछोगे कि क्यों प्रेशर ड्रॉप होता है, तो प्रेशर ड्रॉप ओनली टेक्स प्लेस इन थ्रॉटलिंग वाल्व ओनली फॉर सम फ्रिक्शनल लॉसेस. प्रेशर ड्रॉप टेक्स प्लेस ओनली बिकॉज ऑफ सम लॉसेस इन केस ऑफ थ्रॉटलिंग वाल्व. सो जैसे कि एग्जाम्पल्स क्या है, एग्जाम्पल्स ऑफ थ्रॉटलिंग वाल्व्स. व्हाट आर द एग्जाम्पल्स? इस एग्जाम्पल्स में जैसे कि ओरिफिस हो या पार्शियली ओपेंड valve, adjustable valve, porous plug, then capillary tube. All these are examples of throttling devices. जैसे कि जहाँ सम फ्लो तो होता है लेकिन वो रेस्ट्रिक्टेड मैनर पे होता है. और इफ जैसे you will study in fluid mechanics that there is a circular hole and in that there will be some losses either due to sudden expansion or sudden expansion or frictional losses will be there. So for that reason pressure of the fluid will decrease from inlet section to outlet section. Similar thing happens with the partially opened adjustable valve. And porous plug जो होता है वो स्पॉन्ज लाइक मटेरियल होता है. एंड कैपिलरी ट्यूब्स जो हमारा डोमेस्टिक रेफ्रिजरेटर में यूज होता है. जैसे कि ये हो गया हमारा एग्जाम्पल में, ये हुआ हमारा एडजस्टेबल वाल्व. इसको अगर हम पार्शियल ओपन करेंगे तो फ्लो जो होगा वो रेस्ट्रिक्टेड मैनर पे होगा, यूजुअल फ्लो नहीं होगा. सो प्रेशर जब रेस्ट्रिक्टेड वे में फ्लो होगा मतलब प्रेशर ड्रॉप विल टेक्स प्लेस. एंड दिस इज द पोरस प्लग. दिस इज ऑल्सो एन एग्जाम्पल ऑफ थ्रॉटलिंग डिवाइस. And there are some pores, small holes, small pores are there, and this is sponge like material. So this is also, there will be some restricted flow in this sponge like material. So this is an example of throttling device also. And another example is capillary tube, that is a small dia tube. This is also, these three are examples of throttling devices. So here प्रेशर ड्रॉप तो होता ही होता है. सो व्हाट अबाउट टेम्परेचर? क्या टेम्परेचर में ड्रॉप आता है हमेशा? और व्हाट हैपेंस दैट वी विल नो. यू नो प्रेशर जो ड्रॉप होता है, प्रेशर ड्रॉप is often accompanied by a large drop in temperature. Temperature of fluid also decreases with pressure, decrease in pressure. So drop in temperature. So that's why this throttling valve is used for refrigeration and air conditioning purposes, where pressure decrease in pressure of the refrigerant in case of refrigerator is required, and along with that decrease in saturation temperature is also required. That's why, since pressure drop in throttling device is more often than not accompanied by a large drop in temperature, throttling devices are suitable. Throttling devices are commonly used because in these cases both pressure drop and temperature drop takes place. That's why these are suitable for, these are commonly used for refrigeration and air conditioning and air conditioning applications. But you see, not always there is a decrease in temperature. Sometimes also there may be some rise in temperature, and whether it is going to increase or decrease, that can be decided by a coefficient called Joule-Thomson coefficient, that we will study later on. Joule-Thomson coefficient. Joule-Thomson coefficient, which is nothing but mu J, which is dou T upon dou P. How the temperature will vary with respect to pressure, that we will study later on while studying about Joule-Thomson coefficient. There may be, the important point is that not always, there is not, pressure drop is not always accompanied with drop in temperature. Sometimes there may be some rise in temperature with drop in pressure in throttling devices also. प्रेशर तो ड्रॉप हमेशा होगा थ्रॉटलिंग डिवाइस में, लेकिन sometimes there may be also temperature rise of the fluid that passes through it, and more often than not there is a decrease in temperature, but sometimes also there may be some temperature increase of the fluid that passes through it, and that will be determined by Joule-Thomson coefficient. So what are the applications, main applications of throttling devices? Applications of throttling devices. So application जैसा हुआ, first application vapor compression refrigeration system, that you will study in your refrigeration and air conditioning part. You know, this is VCRS, vapor compression refrigeration system. ये VCRS में यूज होता है. थ्रॉटलिंग valve is used. Throttling valve is used. This is another example of throttling device. This throttling valve is used to reduce the pressure of refrigerant. ये refrigerant है working fluid that operates in a refrigeration cycle. Refrigerant is nothing but a working fluid that flows through the refrigeration cycle. So throttling valve in vapor compression refrigeration system, what does it do? It is used to reduce the pressure of refrigerant from condenser pressure to evaporator pressure. So this condenser pressure is always on the higher side, and evaporator pressure is always on the lower side. So this function of the throttling valve is to reduce the pressure of refrigerant from this condenser pressure to evaporator pressure. And there may be some other applications like This throttling device is also used, throttling device is also used in throttling calorimeter, throttling calorimeter. And this throttling calorimeter, which is a device which is used to measure the dryness fraction or quality, which you will come to know while studying the pure substance, that in a liquid vapor mixture there is a term called quality, which represents the mass fraction of the vapor in a liquid vapor mixture. So to determine that, throttling calorimeter is used. Throttling calorimeter is a device which is used to measure the quality of a liquid vapor mixture, which is used to measure dryness fraction or quality. They are both same thing. They refer to same thing. Quality of dryness fraction or quality is determined for a liquid plus vapor mixture. Liquid plus vapor mixture. And it quality always varies between 0 and 1. It cannot be less than 0 and it cannot be greater than 1. So in this throttling calorimeter also throttling device is used. So throttling calorimeter is a device which is used to measure the dryness fraction or quality of a liquid plus vapor mixture. So these are the applications. Now we will go for mathematical derivation of steady flow energy equation for throttling device. You see, mathematical derivation, we know that the general steady flow energy equation we have already studied, but what will be the equation? What will be the steady flow energy equation, particularly for throttling device? So equation varies from device to device because some assumptions vary, conditions vary. That's why the general steady flow energy equation assumes different forms for different steady flow devices. So what will be the case for this throttling device? Suppose we will take the example of this porous plug. You see, porous plug, suppose this is the section 1, this is the inlet section and this is the 2. You know, porous plug is a steady flow device. So this is the upstream side and this is the downstream side. Here fluid enters and here fluid flows from this to this direction. In this direction the fluid flows. So this is obviously the upstream side and this is the downstream side. And pores are here. Pores are here means there is some reduction in cross-sectional area. According to continuity equation, we know that product of area and velocity, suppose velocity we will take capital V, is equal to constant. So here you see this is at the upstream side, area at the upstream side and area at downstream side are same. So the velocity here and velocity here will be same. But what about the velocity here? Velocity will be higher here because there is the reduction in area. क्योंकि यहाँ some pores are there, obviously, so there is a reduction in cross sectional area. Here is the obstruction, that's why it is a throttling device, because these pores result in a restricted flow, otherwise the flow would have been smooth. So here, due to that presence of pores, there is a reduction in cross sectional area. So that means if area decreases, so velocity here, this is suppose 3, section 3, so velocity at 3 will be obviously higher than V1 और V2, क्योंकि V1 इज इक्वल टू V2। यहाँ अगर 5 मीटर पर सेकेंड है तो यहाँ भी 5 मीटर पर सेकेंड वेलोसिटी होगा, लेकिन सेक्शन 3 पे यहाँ विद इन दैट पोरस प्लग obviously the velocity will be higher because the cross sectional area is less. So but since we are analyzing for this upstream and downstream side, we can take that the velocity remains constant throughout by neglecting the velocity here. Since we are analyzing the steady flow device and this is the upstream section and this is the downstream section, here the velocities are same, and of course there may be some increase in velocity in between, but that change if we can neglect, then we can assume that between these two sections the change in kinetic energy is negligible. यहाँ velocity में increase होता है, लेकिन we can neglect that because we are considering only the inlet and outlet section, upstream and downstream section, जहाँ velocity same होता है, क्योंकि area of cross sectional area at 1 is same as cross sectional area at 2. So that's why we can neglect that increase in velocity here at this point or at this section. So we can assume that there is no change in kinetic energy, and the potential energy change can also be neglected. If there is any change in potential energy, that can be neglected because that will be quite small because it is horizontal. So what will be the equation? You see, जो general equation होता है, so you know steady flow energy equation can be expressed in two forms. One is in rate form and another is in per unit mass form. Suppose we will go for a rate form. We know that in the rate form the steady flow energy equation is dq upon dt. T here refers to time plus m dot h1 plus v1 square by 2 plus gz1 is equal to dwcv by dt. Here work is shaft work or electrical work, we know that, but there is no boundary work. So plus m dot h2 plus v2 square by 2 plus gz2. So I can write in this way also. This is q dot dq upon dt. I will write q dot. There is no problem in it. Q dot plus m dot. Since mass flow rate at inlet is same as mass flow rate at outlet, I have to write m dot for both cases. So m dot h1 here subscript 1 refers to the section 1. So I am analyzing between the sections 1 and 2. Here I will use the subscript 1 for every term like enthalpy, velocity, etc. And for 2 I will use the subscript 2. So q dot plus m dot h1 plus v1 square by 2 plus gz1, and this equation is in the rate form. W dot cv plus m dot h2 plus v2 square by 2 plus gz2. So this is the rate form. That means every term in this equation will be expressed in terms of kilojoule per second or joule per second. Rate form में है kilowatt. Every term in this equation will be having unit like kilowatt or watt simply. So I can write this as q dot is equal to w dot cv प्लस m डॉट, ये जो टर्म को हम यहाँ ले आएंगे. Obviously we have considered that there is a single stream of fluid entering and single stream of this is a single stream case. मतलब m dot h2 minus h1. I will take this whole term to this side. M dot h2 minus h1 plus v2 square minus v1 square divided by 2 plus g z2 minus z1. So this is the equation. But you see, यहाँ totally W dot CB will be 0. Why? Because there is no shaft here in case of throttling device. Shaft is there only in turbine and compressor. So W dot CB is 0. There is no shaft work. Neither the work is produced nor any work is consumed. So shaft तो लगा नहीं हुआ है ना. Q dot is equal to this much. So I can write this like this also. M dot H2 minus H1, ये अगर मल्टीप्लाई करेंगे तो आई कैन राइट दिस डेल्टा H डॉट. मतलब M डॉट का यूनिट होता है kg पर सेकेंड और H2 माइनस H1 जो चेंज इन स्पेसिफिक एंथैल्पी उसका यूनिट होता है किलो जूल पर kg. सो ये कैंसिल हो जाएगा, यूनिट आएगा किलो जूल पर सेकेंड पे. सो ये होगा डेल्टा H डॉट, डेल्टा कैपिटल H, टोटल एंथैल्पी, रेट ऑफ चेंज ऑफ टोटल एंथैल्पी किलो जूल पर सेकेंड में आएगा, प्लस डेल्टा चेंज इन काइनेटिक एनर्जी डॉट. ये जनरल इक्वेशन के बारे में, ये जनरल इक्वेशन फॉर्म में है, डेल्टा पोटेंशियल एनर्जी डॉट. लेकिन हम तो ये assumption लिए कि there is negligible change in kinetic energy and potential energy. In this case there is negligible change in kinetic energy and potential energy. So these two terms will be reduced to 0 in this case. So now the equation left out is, now this equation reduces to this equation. This is suppose your general equation 1. Suppose this is how the rate steady flow energy equation in rate form is written. So this equation 1 now reduces to Q dot and this is delta H dot. So this is the equation applicable for throttling device. This is the equation, steady flow energy equation applicable for any throttling device. Of course, for small throttling device the equation may be different, and for big throttling device the equation will be different. So that will come just after this. So but the equation for throttling device is, this is the general steady flow energy equation. This is the overall equation, general equation, but this is the general steady flow energy equation for any throttling device. Q डॉट इज इक्वल टू डेल्टा H डॉट. अगर हम पर केजी मास फॉर्म में लेंगे तो ये इक्वेशन हो जाएगा Q डॉट डिवाइडेड बाय M डॉट इज इक्वल टू डेल्टा H डॉट डिवाइडेड बाय M डॉट. सो ये हो जाएगा स्मॉल q इज इक्वल टू डेल्टा H. अगर पर केजी मास फॉर्म में लेंगे, पर जिसमें हर जो टर्म होगा उसका यूनिट होगा किलो जूल पर केजी या जूल पर केजी. तो हीट का यूनिट होगा किलो जूल पर केजी फ्लूइड में कितना हीट आ रहा है या जा रहा है, क्यू, स्मॉल क्यू डॉट में अगर एम डॉट मास फ्लो रेट को डिवाइड करेंगे तो ये आ जाएगा. डेल्टा एच इज चेंज इन स्पेसिफिक एंथैल्पी. सो ये किलो जूल पर केजी पे आएगा. यूनिट ऑफ स्पेसिफिक एंथैल्पी इज kilojoule per kg. Suppose this is 2 dash, this equation, this is also applicable. Q, small q is equal to delta small h, yeah, capital Q dot is equal to delta h, capital delta H dot. That can be equations. So what are the assumptions that we made while deriving this equation? Assumption is there is negligible. So only assumption that we made here is negligible change. There is negligible change in potential energy and kinetic energy. Potential energy and kinetic energy. So we'll think about some special cases. Analysis for small throttling device, small throttling device, small throttling device. Throttling devices are usually small. Throttling devices are usually small with some small surface area. So what will be this equation? What form this equation will assume for small throttling device? Because most of the throttling devices are small with small surface area or with less surface area. So you know that predominantly, suppose in this case, this porous plug, if heat loss is there either from the device to the surrounding or from the surrounding to, or if there is heat transfer from surrounding to the device, the predominant mode of heat transfer in this case is convection. That is Q dot is equal to H bar. This is Newton's law of convection. H bar is average heat transfer coefficient, A is surface area, and delta T is the temperature difference between the body and the surrounding. Here the temperature difference between the valve and the surrounding. So it will obviously depend upon surface area, and for a small throttling device, area will be small. Obviously the Q dot will be then small. Q dot will be negligible for small throttling device. एंड तुम पूछोगे कि Q डॉट लेस हो सकता है, देन व्हाट अबाउट Q? Q डॉट मीन्स रेट ऑफ हीट फ्लो, किलोवाट. लेकिन व्हाट अबाउट द टोटल हीट फ्लो? टोटल हीट फ्लो विल डिपेंड अपॉन टाइम. Total heat flow will depend upon time. This is time, and this should not be confused with delta T. This is the capital T stands for temperature, and suppose time. So like in T will in this case will also be very less. T means since the device is very small, so there will not be enough time while fluid is flowing, because the fluid flows through the device with very little, within a very little time period. So that's why the time is of course required for any heat transfer to take place. So since this is a small device, there will not be enough time for any kind of heat transfer to take place either between the device and either from the device to the surrounding or from the surrounding to the device. So that's why time there will not be enough time for any kind of effective heat transfer to take place. So that's why the Q or Q dot both can be assumed to be 0. So now our general steady flow energy equation for the throttling device was equation 2, Q dot is equal to delta H dot, or small q is equal to delta H. And for this small case, Q can be assumed to be 0. So now the equation 2 reduces to delta H dot equal to 0, especially for small throttling device, or I can write this small delta H, that can be 0. Small delta H0 means H1 specific enthalpy at inlet section is equal to specific enthalpy at outlet section. Here in this case, specific enthalpy at upstream is equal to specific enthalpy at downstream. That means H1 is equal to H2. Since enthalpies are same at both inlet and outlet, that's why throttling devices are also known as isenthalpic devices. Since the enthalpies at inlet is equal to enthalpy at inlet, specific enthalpy हो या total enthalpy, since delta H dot is equal to 0, total enthalpy भी ले सकते हैं. H1 dot is equal to H2 dot. मतलब since specific enthalpy at inlet is equal to specific enthalpy of the fluid at outlet, so throttling devices can be called as isenthalpic devices. So what happens when we analyze throttling process for an ideal gas? When the fluid that passes through this throttling device is ideal gas, so what will happen? Ideal gas undergoing throttling in small throttling device with negligible changes in kinetic energy and potential energy. You see, so अगर जो फ्लूइड passes through the small throttling device जैसे कि ये हुआ, if this fluid is ideal gas, then what will happen? So we just derived that the equation is H1 is equal to H2 for a small steady flow energy equation. For a small throttling device is H1 is equal to H2. But if the fluid that passes through that small throttling device is ideal gas, what will be the result? What will be other interpretations? So you see, for an ideal gas, we know that H is a function of temperature only. Enthalpy of an ideal gas is both enthalpy and internal energy. Specific enthalpy and specific internal energy are functions of ideal gas. For ideal gas, and specific enthalpy and internal energy are functions of temperature only. So I can write H as a function of temperature. Since H1 is equal to H2, I can write T1 is also equal to T2. Temperature at inlet is equal to temperature at outlet. Since temperature at inlet, suppose this case, this is an ideal gas when passes through this throttling valve, adjustable valve, here ideal gas. Since H1 is equal to H2, since H is a function of temperature, I will be having T2 is equal to T1. यहाँ जितना टेम्परेचर होगा इनलेट पे और अपस्ट्रीम पे, यहाँ डाउनस्ट्रीम पे, सपोज the fluid is or ideal gas is flowing in this direction. So this is the upstream side and this is downstream side. Since H2 is equal to H1 is the steady flow energy equation that we derived just right now for small throttling device. This is the general equation. Since it is an ideal gas, T1 will be equal to T2. Not for all fluids, only for ideal gas, because for ideal gas enthalpy is a function of temperature. If it had been a liquid, then T2 would not have been same as T1. If it had been a real gas, the case may be different. But for an ideal gas, enthalpy is a pure function of temperature only. So that's why since H1 is equal to H2, we can say T1 is equal to T2. And since T1 is equal to T2, we can also write, you know that specific internal energy is also a function of temperature. So that means since T1 is equal to T2, I can write U1 is equal to U2. U1 equal to U2. U1 is equal to U2. And we know that H is equal to U plus PV. Suppose this is equation 3 and this is 4. So this equation is already there. Suppose this is 3. H1 is equal to H2 where that was not numbered. So now this is suppose equation 3. So now this is equation 3. So U1 is equal to U2 is equation 4 suppose. So since U1 is equal to U2, also H1 is equal to H2. We know that H is equal to U plus PV. By putting that relationship in this equation 3, I can write U1 plus P1 V1, where P is the pressure at inlet section or at upstream section and small v1 is the specific volume at upstream section, is equal to U2 plus P2 V2, because we know that small h is equal to U plus PV. Since U1 is equal to U2, putting this equation, substituting this equation 4 in this, suppose this is 5, what we will find is P1 V1 is equal to P2 V2. P1 V1 is equal to P2 V2. Flow work, this is product of pressure and volume is flow work. So flow work at inlet is equal to flow work at outlet. But suppose V2 is twice of V1. Since it is a gas is a compressible fluid, so specific volume will change from place to place. In case of incompressible fluid, specific volume or density will not change. Since it is an ideal gas, specific volume or density, both are related because density is reciprocal of specific velocity volume. This is small v is specific volume. So if suppose v2 is 2v1, 2 small v1, then what will happen? So p2, from this p2 will be half p1. So pressure will be less at downstream as compared to that at upstream. That is the case with throttling device. So pressure obviously will at downstream will be less than upstream, and there will be change in specific volume. So for ideal gas, this is a special case. That relationship is T1 will be equal to temperature T2, temperature at inlet and outlet will be equal, and product of specific volume and pressure will also remain same at both the sections. We have to use these equations for solving some questions. You have to remember this. For a specific case of ideal gas, this T1 will be equal to T2, temperature will be constant, and product of pressure and specific volume will be constant at both these sections. And if it had been a big throttling device, so big throttling device में what will be the equation? If throttling device is suppose big, मतलब if there is some large surface area, device is having large surface area just like your capillary tube that is used in domestic refrigerator. So क्योंकि इक्वेशन हमारा जो है Q is equal to h bar a delta t, that means if the device is with a large surface area मतलब you can't neglect Q. So जो इक्वेशन हम डिराइव किए फॉर जनरल थ्रटलिंग डिवाइस, दैट इज Q is equal to delta h small h. So we cannot neglect Q in this case since this is a throttling device. There will be some significant heat flow is possible. That means there may be some heat transfer taking place. So that's why for that case equation will be Q is equal to delta h. But for small throttling device, delta h, this is for big, this is for small, or H1 is equal to H2. And for ideal gas, small and ideal gas, this is small and the fluid is, if it is ideal gas, then the equation will be T1 equal to T2, and since H1 is equal to H2, for an ideal gas this will be T1 is equal to T2 and P1 V1 equal to P2 V2. So this is for ideal gas, or Q dot is equal to, for especially for a big throttling device, delta H dot. This you cannot take 0 for a big throttling device.